Hello, in this video we study orthonormal basics and we learn how to apply Gram-Schmidt process to get an orthonormal basics from any basics of a space. Alright, so let me remind you about previous lectures. So previous lectures we study inner product, right? Inner product. Uh, that is some maps, like if you have vector space V, so you consider map V Cartesian product with the V into R, and if this map satisfies three properties, uh, then this is an inner product. Okay, let's say the first property is if you interchange the position of U and V small, and that is also V and U, the value does not change. The second one, so you multiply C with the U and V in here, you get the same. You can take C in or out. And then the last property is U and U, in the product of U and U is always greater than or equal to 0. And the equality happens if and only if U is equal to 0. All right, and we also study some properties of inner product spaces. Let me remind you about that before we move to this section. Um, we study the length, right? The length of a vector, right? With respect to some inner product space, that is just the norm of U. That is U inner product, and then apply square root. This is interesting. Apply square root in here. Okay. So and then once we have length of a vector, you can define distance between two vectors. That is just the norm of U minus V, right? Of course, this is with respect to our inner product. And then once you have distance, you can measure the angle between them using the following formula: cosine of theta, where theta is the angle between U and V, equal to inner product of U and V divided by norm of U, and then divide by the norm of V. And you can determine orthogonality, right? We say that two vectors U and V are orthogonal if the inner product of U and V is equal to 0. Or, in this case, theta is just pi over 2, right? So now we have right to talk about orthonormal and orthogonal and orthonormal basics. Right here, you can see orthogonal and orthonormal basics, because that is really important. I repeat several times about basics in R2. Let's say this in R2, right? So you have any vector. Okay, the standard basic is 1, 0, and 0, 1. But again, if you pick any two not collinear vectors, they will form a basics of R2. So this guy, even they are not orthogonal, they still form basics. But the problem is when you work with 1, 0, 0, 1, it seems to be easier and very convenient. But when you work with some basics like U and V in here, it's not convenient at all, because you need to express any vector as a linear combination of U and V, right? And that's not good at all. Since if you have orthonormal basics 1, 0, and 0, 1, any vector that is just x 1, 0 plus y 0, 1. You see the x and y in here, are just coordinates of this vector in this basics. So everything is very convenient. That's why when we have a basics, right, we really want to get an orthonormal basics. Orthonormal means orthogonal basics, and norms of vectors in this basics is 1. That's why you have normal, right? Ortho means orthogonal, and normal means norm 1. So orthogonal means all vectors in this basis are perpendicular, like 1, 0 and 0, 1 in here. You see, like 0, 1 and 0, 1 here. And of course, the norm of 1, 0 and the norm of 0, 1 are 1. So that's why, it's very convenient to work with them. Make sense? So that is the main purpose of today's lecture. We'll learn how to make that. All right, so let's talk about orthogonal and orthonormal sets, right? Here's the definition. A set S of a vector in an inner product space V is orthogonal if every pair of vectors in S is orthogonal. And if each vector in the set is a unit vector, means vectors of norm 1, then S is orthonormal. I just explained you about that. Right? For example, so like you have like S is the set of V1, V2, Vn. So please forgive about this because in this case they just write the indexes, right? V1, V2, and Vn. Another definition of orthogonal and orthonormal sets like can be rewritten in the following form. Orthogonal means all. If you pick arbitrary vectors v1, vz, they are orthogonal, means that their inner product is 0, and orthonormal. So the first condition is inner product is 0, and the second condition is norm equal to 1. All right. So when you work with the basics, yes, actually we really want to have orthonormal. But from this definition, probably you can guess. In order to get orthonormal, at first you need to get orthogonal, right? Because once you have orthogonal, the first condition in orthonormal basics satisfied. And then in order to get unit vector, you just divide each vector by their norms, so you get unit vector. So let me remind you about that, right? Unit vector. So if you get some vector u, you divide by the norm of u, so that is already unit vector because the norm of this vector is 1. So the problem to find orthonormal basics just reduced to the problem to find orthogonal. And the second step is pretty simple. Just divide all vectors in that orthogonal basics by their norms, right? Okay. Let's move to the next lecture, the next slide. So now, the first example, a non-standard orthonormal basics in R3. So they ask us to show that the set is an orthonormal basics in R3. So that means we need to check two conditions, right? The first condition, all vectors are orthogonal with each other. The second condition, norms of all vectors is 1. Okay, so let's say you can see right here v1 and v2. Okay, let me go back to previous lecture so we can explain in here. It's easier to follow. All right, so you have v1, that is v1. That is v2, that is v3, right? So you consider inner product, but the inner product in R3 in this case just dot product. So if we don't say anything about new inner product, we suppose we have dot product, okay? So you consider dot product of v1, v2. What is that? So you get 1 square root of 2 times negative square root of 2 over 6, right? Plus 1 over 2 times square root of 2 over 6, and then plus 0. And you can see from this term and these terms, they are different only in the size. So, they cancel them out. You get 0 in here. Similarly, you can get v1 and v3. What's that? That is 1 square root of 2 times 2 over 3. Okay. Plus 1 over square root of 2 times negative 2 over 3. This is also 0. The last term is just 0, so I don't write this. And then you consider v2, v3. That is negative square root of 2 over 6 times 2 over 3 minus, or I say plus, let's say this, square root of 2 over 6 times negative 2 over 3. And then plus 2 square root of 2 over 3 times 1/3. And when you simplify everything, you get 0 right away. Okay, so that is 0. So that means, this set is orthogonal set, right? It says orthogonal set. And now, I tell you right away, if they are orthogonal, that means this set is linearly independent. Don't forget about that. If they're orthogonal, the auto will be linearly independent. Okay? Independent. Okay? So, because we are talking about basics of R3, we have 3 vectors and they are linearly independent. So that means they form basics, right? And now we need to check if they will form an orthonormal basics or not. So that means the second condition, norms of all vectors is just 1. So you can check that easily from here. Of course, this has norm 1, right? I write here norm of V1 is just equal to 1. And if you calculate the norm of this vector, this should be 1 too, and this is also 1. Let me show you 1, right? Let's say the norm of V3, what's that? That is square root of 2 over 3 square plus negative 2 over 3 square plus 1/3 square, right? So basically that is, square root of 4 over 9 plus 4 over 9 plus 1 over 9, which is square root of 9 over 9, right? And that is 1. Similarly, you can show that the norm of V1 and V2 is 1. So overall, this set is an orthonormal basics of R3. Okay, so in this example, we learn how to test, how to check if a set is orthonormal basic. First, we need to check basics, right? We need to check basics. So if they are orthogonal, so that means, they form basics because we have 3 vectors in 3-dimensional space. And then we check orthonormal, just check the norm. All right, let's move to, the next example. Let's consider the set C0 2 pi. That means the space of continuous function on 0 to 2 pi. Okay, and we learn the inner product in C is the following. Just take integral from A to B, in this case from 0 to 2 pi, right? And then, integral of the product of f and g. Now we need to show that the set S1 sine cosine sine 2x cosine 2x and so on sine nx and cosine nx is orthogonal. I don't say anything about basics in here, right? But let's show that S is orthogonal. So that means we need to check that, in the product of any 2 functions in S is 0. Okay, so it means in the product of, let's say, if you take f and g, let's say f and g in S, in the product of f, s, and g should be 0. That's it, right? And we, of course, we need to use this definition. All right, so how do that? Here is how we can check it. First, we pick 1, right? And you check in the product of 1 and sine of nx for any n. Because, you have sine 1x, sine 2x, and sine 3, and so on, and sine nx. So, I can write in here, this equal to for any n, right? Equal to 0 for any n. It's obvious because in the product of 1 sine and x is integral from 0 to 2 pi, right? 0 to 2 pi, and then product of 1 and sine of nx. So that means just integral from 1 to 2 pi of sine of nx. And what is antiderivative of sine of nx? The antiderivative of sine of nx is what? that is 1 over n cosine of nx, right? With the negative in here, right? And then you evaluate this function from 0 to 2 pi. So you plug 0 and 2 pi into cosine of nx. You get the same value because, cosine of 0 is 1, cosine of 2 pi nx, 2 pi n is also 1. So when you subtract them, you get 0. Makes sense? You do almost the same thing for inner product of 1 and cosine of n. And we know that antiderivative of cosine of nx is just 1 over n sine of nx, right? And then this evaluated from 0 to 2 pi. At 0, sine of 0 is 0. At 2 pi, sine of 2 pi n is also 0. So basically, this is also 0, right? That means 1 is orthogonal to sine nx and cosine nx for any n. Which is good. The next, we need to check 3 more cases. Okay, this is the first case, the second case, and then the third case. So we consider inner product of sine mx cosine nx. So what is that? That is integral of, sine mx and cosine nx. I remember, in calculus 2, we learn about, trig functions and integrals, right? So I hope that you know how to go from product of sine cosine to sum or difference. Okay, so let me remind you about that before we discuss in detail, right? Here we have sine cosine, so we have the following formulas. I just writing here. If you have sine of x plus sine y, right? So that is nothing but 2 times sine, 2 times sine, sine 2 times sine of x plus y over 2 times cosine of x minus y over 2, right? And that is our case. So that means that is how you go from sum to product. And if you want to go back, it's okay. I can write sine of mx times cosine nx. What is that? That is sine of, I write here, sine of mx plus nx. Okay, and then plus sine of, we have sine cosine, so we have mx minus nx. Look at this. Let's verify this, right? Just be careful. So if we apply this formula for mx plus nx and then mx minus nx, so you get exactly what you have in here. Makes sense? For example, x plus y over 2 is what? Mx plus nx plus mx minus nx over 2. So that is exactly sine of mx, right? And if you consider x minus y, so you get exactly nx. So everything is good. Now, you will evaluate this integral. So you break that into 2 integrals, right? The first integral is integral from 0 to 2 pi. I write here sine of m plus n x dx. And of course, this is 0, as we have seen, right, previously. Right here in the first case. You see this? In the first case right here. For the second integral, you can see, that is integral from 0 to 2 pi and sine of m minus nx. This is also the same. The integral is 0. So overall, sine of mx and cosine, or the inner product of sine mx and cosine nx is 0. That means these two functions are orthogonal for any m and n. That means we just verify the first identity. Make sense? So for the second identity, we use also this, almost the same idea, but we also need to go from product to sum. Look at this. We need to go from product to sum, but with different formula. Okay. I hope that I will write some. I will write a formula for you, and you try to verify. Okay. So for psi and size, I have the following formula. I have cosine of A, I write this, minus cosine of B is equal to 2 times negative 2 times sine of A plus B over 2 times sine of A minus B over 2. So you apply this formula for mx and nx, you will break your integral into two integrals. And then at the end, you get, similar situation right here. And then the second situation is also verified. And the same situation for the last one, but again, you have another formula. Let me write that for you. Here we have cosine, cosine. Yeah, how to get cosine, cosine. So that is cosine of A plus cosine of B is equal to 2 times cosine of A plus B over 2 and cosine of A minus B over 2. Make sense? So, that's it. It's pretty easy, I would say that. All right. So let's move to the next. That's how they show you. Okay. So I think I can skip this. Now, this theorem says about any orthogonal sets are linearly independent. I just show you about that. So we accept this theorem without proof, but the proof is pretty easy. Okay, so I will skip this. And then if V is an inner product space of dimension n, and you have an orthogonal set of n non-zero vectors, so that set should be a basis of V. That's what we just used in the very first example. Okay. Now let's consider the following example. So that the set S is a basis for R4. You have 4 vectors. Okay. You have 4 vectors. And you need to show that this is a basis of R4. Pretty easy. We know how to do that, right? Even in previous chapter. So traditional, I will do the following one, right? I'll do the following one. I write in the matrix form. I have 2, 3, 2, negative 2. I have 1, 0, 0, 1. I have negative 1, 0, 2, 1. And then I have negative 1, 2, negative 1, and 1, right? So this matrix has all rows as V1, V2, V3, V4. If we show that the rank of this matrix is 4, that means 4 vectors, 4 rows are linearly independent, right? Then, rows are linearly independent. That means they will form a basis of R4. Okay? So I hope you can do that easily. But now we're studying orthogonality. Okay? So they ask us to use orthogonality to test if these 4 vectors form a basis of R4. So probably they ask us to test that if they are orthogonal manually orthogonal means they are orthogonal with each other. Let's say that, right? So yeah, we just need to check the inner product. We just need to check inner product of V1, V2, V1, V3, V1, V4 equal to V2, V3 equal to V2, V4 and equal to V3, V4, and all these inner products are 0. And that means, they are orthogonal. And S is an orthogonal set. 4 vectors of orthogonal, right? Four orthogonal vectors in R4 will form basics. Is it? Uh, so you can see that easily. Here's the solution. So you consider V1, V2. So you have 2 plus 0, 0 minus 2. Let me repeat that because in the previous slides maybe we did not catch, right, the vector. So let me explain one product in here. So v1 is 2 3 2 negative 2 and v2 is 1 0 0 1, right? You can see dot product, you get 2 times 1 plus 3 times 0 plus 2 times 0 plus negative 2 times 1. That is 0. Is it? So just consider all dot products and you see, yeah, all of them are 0. That means the set S is orthogonal, and that is a basics. Okay, so not only basics, in this case they are orthogonal basics of R4. Make sense? Okay. So this is the one which is very important. Say, yeah, I just explained in the very first slide of this lecture, right? The motivation why we need orthogonal and orthonormal basics in a vector space. And here's the case. If B is an orthonormal basics of an inner product space. So I say, yeah, this guy is an orthonormal basics. Then the coordinate representation of any vector W relative to B or with respect to the B is this one. So you express W as a linear combination of V1, V2, Vn, right? And here's coordinate. You see this? It's just, coordinates of W. It's just inner product of W with each vector in this basics, in orthonormal basics. So that's why it is very convenient to work with orthonormal basics, because when you want to express any vector as a linear combination, right, of vectors in a basics. So in order to find the coordinate, you don't have to solve the system linear equation. You remember that? So okay, if you have some vector v, right, and you say, yeah, you want to solve, you want to express v as lambda 1 v1 plus lambda 2 v2 and so on, lambda n vn. So basically solving this system, you need to you find the coordinate, right? The coordinate lambda 1, lambda 2 and so on, lambda n. So those coefficients or the solution of this system is coordinated. But now if you work with orthonormal basics, you don't have to solve the system. You don't have to solve the system because that takes time, and that I would say cost expensively, right? Means you have to calculate a lot. But now once you have orthonormal basics, you only need to find dot product. Dot product, inner product. You just need to find inner product, right, of W with each vector v1, v2, and vn. So you find coordinates of W in v1, v2, vn right away, and it's very fast. You see, this theorem is also easy to prove. You can see the proof in the textbook. So since in this course we don't do proof, but try to understand the idea, how to have that. Okay, all right. So if you consider the picture, you would see the following one. Let's say in R2, right? In R2. So like in R2 we have standard basics 1 0 and 0 1. But sometimes I don't have this standard basic, right? I have, okay, let's say I have unit circle in here. So you can pick two arbitrary point in the unit circles in here, right? And if they are orthogonal, so they will form an orthonormal basics. Is that correct? So this guy and this guy will form an orthonormal basics. And when you go from one basics to another basics and you want to see, the coordinate, you just need to find that inner product of your vector with respect to new basics. So you have coordinate of them. So everything is very fast. All right, let's consider the following example. Find the coordinate matrix of W relative to orthonormal basics B for R3 as below. So B is with V1, V2, V3, and B is given, like this. You can go ahead to check if B is an orthonormal basics, right? Okay, let's do this first, and then before we express W as a linear combination of B, and try to find, coordinate of W. So the norm of V1 is 1, is it correct? So you have square root of 3 over 5 square plus 4 over 5 square plus 0 square. And that is 5 square over 5 square, which is 1. You see? Similarly, you can check that the norm of V2 and V3 are also 0. So I erase this, okay? So yeah, they are unit vector. And you can see that they are orthogonal. For example, you consider dot product of V1 and V2, you get 3 over 5 times negative 4 over 5. And here 4 over 5 times 3 negative over 5. You sum them up, you get 0. Right? You get 0 right away. That means V1 and V2, are orthogonal. And so you can do like V1, V3 is obvious between V1 and V3, and it's also obvious for V2, V3. Because in V3 you have 2 zeros, okay? It's easy to calculate. Now we just convince ourselves that yes, actually B is an orthonormal basics for R3, right? And now we need to find coordinate matrix or just coordinates of W with respect to B. No problem. I just need to find W V1. I just need to find W V2. I just need to find W V3. I mean, here is inner product. In this case, dot product. I don't have to solve the system, you see? So I just write like this. So I can find I write 5, negative 5, and 2. Inner product with 3 over 5, 4 over 5, and 0. So you get 3. You multiply 5 with 3 over 5, and then negative 5 with 4 over 5, plus, minus 4. And then plus 0, which is negative 1. And then you calculate the dot product of W with V2, 5, negative 5, 2. Dot product with negative 4 over 5, 3 over 5, 0. So you get negative 4 minus 3 plus 0, which is negative 7. And then you need to have this guy 5, negative 5, and 2 times 0, 0, 1, which is 2. You see, you already have coordinates of W with respect to the B right away. You don't have to solve the system. Usually, you need to solve this. You need to find the transition matrix, right? The transition matrix. Okay, let's remind you about that. So, how to find a transition matrix? You want to find the transition matrix from the standard to B. You have to solve the following. You write B in here, and then here's identity, right? And so that means you have to find the inverse of the B, right? The inverse of B, where B is what? Where B is, 3 over 5 in here, and then 4 over 5, and then 0. You write vectors V1, V2, V3 in the column form, okay? Negative 4 over 5, 3 over 5, and 0, 0, 0, 1. You need to find the inverse of B, right? And then you apply the inverse of B to the coordinate to the coordinate of W with respect to the standard. That means here you have 5, -5, and 2. So the answer is, this is the coordinate of W with respect to the B. You see, you have to go a very long way. Make sense? If we don't know B is an orthonormal basics or not. But once you know B is an orthonormal basics, you only need to do this in the product. Done. Make sense? So I think I will finish the lecture right here. I hope that you find time to do homework. If you have any questions, please feel free to let me know. In the next lecture, we will jump to Gram-Schmidt process. That is long, pretty long. So if we work with matrices of higher degree, so I would to use the whole lecture for that. Okay. Thank you for watching, and be safe.